Swayam Prabha. Digital India. Educated India.
Hi friends, now we will have a tutorial session which is based on the last 4 classes. In this class, we will solve some numerical problems, and our first problem statement says the gas produced by a steam reformer is exiting at a pressure of 2144 kilopascal and has the following composition. Determine the partial pressure of each component. So, here a table is given, component and molar fraction, that is hydrogen H2O, CO, CO2, CH4 and hydrogen is 0.392, H2O 0.438, CO 0.081, CO2 0.080 and CH4 0.009. So, this is the problem statement, and we have to determine the partial pressure of each component. Mole fraction is given and total pressure is also given. So, we can measure it. Now, let us see. So, what is our step 1? We have to calculate the partial pressure of each gas in the steam exiting the reformer. So, we can use which formula? That is P I is equal to Y I into P, where P I is the partial pressure, Y is the mole fraction and then P is the absolute pressure, the total pressure of the system. So, in our case, what is our P H2O partial pressure of steam? Then that is equal to mole fraction into the absolute pressure. So, absolute pressure is given, that is the total pressure, that is 2144 kilopascal, this into the mole fraction of H2O. How much it is? Mole fraction is 0.438. So, we will write here 0.438 into 2144, it is coming 939.072 kilopascal. Similarly, for carbon monoxide, the mole fraction of carbon monoxide into total pressure. So, we are having 0.081 into 2144. So, 173.664 kilopascal. Similarly, for carbon dioxide, partial pressure is equal to Y CO2 into P. So, that is equal to 0.080 into 2144. So, 171.52, and similarly for methane, that is equal to 0.009 into 2144, that is equal to 19.296 kilopascal. So, now we will come to problem number 2. So, problem number 2 states that in the steam reforming process for producing hydrogen, part of the reformer exit gas is being burned with 10% excess oxygen from air in order to supply heat for the reforming reaction to occur. The fuel being burned has the following composition, that is component and mole percent. So, H2 41.9%, H2O 5.1%, CO 1.7%, CO2 41.9%, CH4 9.4%. And the combustion reactions occurring inside the firebox are shown below. These are the reaction, that is CH4 plus 2O2 CO2 plus 2H2O, CO plus half O2 CO2 and H2 plus half O2 H2O. The combustion of methane is only 87%. Another condition is methane conversion is 87% complete. So, determine the composition of the gas produced by the combustion reaction, assuming an air composition of 21 mole percent oxygen and 79 mole percent nitrogen. So, in this problem what we have to do? We have to determine the composition of the gas produced by the combustion reaction in the outside of the reforming tube. So, if we have one reformer here, so these are the tubes when the reforming is taking place, then after reforming the gas is going out, and here we are putting some this gas, that is your some part of this gas is recycled back and then it is fed here, and this is burnt in this chamber, this is burnt, and then the burnt gas is going out. So, we have to calculate the composition at this position here. What is the gas composition? And this is the gas composition which is given, it is coming here, and we are also providing oxygen or air, basically air, oxygen plus nitrogen. So, oxygen plus nitrogen is provided here at the outside of this of the tubes, and some gas which this composition is burnt here and it is getting out. Basically, it is a combustion problem, although it is related with reformer, but it is basically a combustion problem. So, mass balance we will do and we will be able to determine the composition of the gas which is going out from this. Then see, for this problem we will take one basis. So, our basis is 100 moles of fuel gas which we are using for the combustions in the outer side of the reformer, and then we will go for mass balance. So, for carbon CH4 balance, methane balance, we have input equal to output plus consumption. Obviously, input equal to output plus consumption, because the CO4 is consumed. So, how much input we had minus consumption is our output, and in this case input is equal to how much 9.4%. So, we have 100 moles. So, 9.4 moles of CH4 we are getting. Then what is the conversion of CH4? 87% of it is converted. So, 0.87 into 9.4. So, that is equal to will be the conversion of it. So, how much methane is remaining in the outlet? So, that is equal to input minus consumption. So, input is our 9.4 and consumption is 0.87 into 9.4. So, this one, so that is equal to 1.222 mole. So, this mole of methane is getting out of the reactor, that is for methane, and since no information is given about the fractional conversion of reaction 2 and 3. So, what are the reactions 2 and 3? CO to CO2 2 and H2 plus half O2, it is giving us H2O. So, these reactions whether the CO is converted completely or not, hydrogen is completely or not. So, we are assuming that the CO is completely converted to CO2 and H2 is completely converted to H2O. So, under this condition how do we get N CO out equal to N H2 out is equal to 0, that means these are completely converted. So, no CO, no H2 is available in the output of this. Then we go for carbon dioxide balance. So, carbon dioxide balance we will again use input plus generation equal to output. In this case carbon dioxide is generated, unlike methane, methane was being consumed, but here carbon dioxide is generated. So, this expression will be used. So, we have to find out the generation. So, how we can determine the generation? We have to see the reactions first. So, what are the reactions? We have these reactions. So, these reactions also give carbon dioxide, this reaction also give carbon dioxide. So, reaction 1 and reaction 2. So, how many moles of methane is used, that many moles of carbon dioxide is also produced, and how many moles of CO is used, that much of carbon dioxide is also produced. Or so, that part we will discuss. So, what is this? Consumed equal to number of moles of CH4 reacted and number of CO reacted. And what is this number of in CH4 reacted, that is 9.4 into 0.87, this part, and what is NCO? The percentage of CO is 1.7. So, out of 100 1.7 moles was present. So, this is this plus this, that is equal to 9.88 moles of CO2 is generated. So, this is the generation of CO2. Then what will be the output of this? Input plus generation. So, what was the input? That carbon dioxide was available in it as 41.9%. So, 41.9 moles was originally available in the inlet of the gas, and now 9.88 moles is generated during the process. So, this plus this will be 51.78 moles of carbon dioxide will be available at the output. Next we see the H2O balance, mass balance for H2O. Then what we will get? Again input plus generation is equal to output, the same formula we will use, and in this case what is the input? Input it is given that 5.1%. So, we are having say 5.1 moles. So, it is given here in this table 5.1. So, that 5.1% we are considering 5.1 moles. The amount of water generated by the chemical reactions will be given by this NH2O generated equal to NH2 reacted plus 2NCH4 reacted, because this was the formula, these are the reactions. So, H2 half O2 H2O. So, how much hydrogen is used, that much H2 is produced, and this is how much methane is used, 2 of that will be the H2O production. So, that is why we will be getting this balance, number of moles of hydrogen reacted equal to number of moles of hydrogen reacted plus 2 into number of moles of methane reacted. So, number of moles of hydrogen reacted, as we are considering that hydrogen is 100% converted. So, 41.9 it is available, as the hydrogen concentration in the inlet gas is 41.9%. So, in out of 100 moles, that is 41.9 moles of hydrogen is available, plus 2 into methane converted. So, methane how much was available, 9.4 into 0.87, that was the conversion, and 2 moles will be generated, 2 moles of H2 will be generated from 1 mole of methane. So, 2 into this will be our H2O generated due to methane. So, this, so overall we are getting moles of H2O generated is equal to 58.256 moles. So, what will be the output, input plus generation? So, input how much we have, 5.1%, and so 5.1 moles we had out of 100 moles, and now we are getting 58.256. So, we are getting 63.356 moles of H2O. Next we will see our oxygen balance, because we have to determine the composition of the outlet gas, which will be containing nitrogen also. So, where from the nitrogen is coming? From the oxygen it is coming. So, oxygen we have used 10% excess, that means I have to determine stoichiometrically how much oxygen is required. So, 10% of that as excess is provided. So, here we need not to consider the how much methane is converted in the reactor in real case, we have to consider stoichiometrically how much oxygen is required for the conversion of the all the methane available in it. So, that we have considered, that we will consider here. So, what is this? In O2, number of moles of oxygen required for methane conversion is your 2 moles of O2 per mole of methane. That is why for complete combustion stoichiometrically we need 2 into 9.4 moles, as 9.4 moles of methane is available originally in the inlet gas. So, 2 into 9.4 equal to 18.8 moles of oxygen is required for the conversion of CH4 to H2O and CO2, and then similarly for CO to CO, carbon monoxide to CO2 conversion, we need half moles of oxygen for 1 mole of CO. This is not CH4, this is CO. So, what we are getting, 1.7 into mole of CO, we have to 1.7 into half of it. So, that is equal to 0.85 moles O2 is required, and then for the hydrogen to H2O production we need oxygen, and that half moles of O2 is required for half moles of hydrogen. Therefore, hydrogen is present 41.9 and all hydrogen is converted. So, half of 49.1, that is 20.95 moles oxygen is required for this reaction. So, what will be our total oxygen consumption? The oxygen consumed for the methane reaction, for the CO and for the hydrogen. So, that is 40.6 moles we have got, that is equal to 20.95 plus 18.8 plus 0.85. So, this is equal to 40.6. So, that moles we are getting. So, now this is the stoichiometric requirement. Now, 10% excess has been provided. So, what was the oxygen provided? So, there is 1.10 into 40.6 moles, that is equal to 44.66 moles. So, that much of oxygen is provided. So, oxygen actually consumed equal to how much? That is equal to 87% for methane conversion. So, 2 into 0.87 into 9.4 plus 100% of carbon monoxide and hydrogen. So, 1.7 into half plus 41.9 into half. So, then it is given to 38.156 moles of O2. So, this 44.66 I am giving, we are giving, and 38.156 moles of O2 is being used for the combustion process. So, remaining will be available in the exit gas. So, 44.66 minus 38.156 equal to 6.504 moles of oxygen will be available. Then what about the nitrogen? So, as we know that nitrogen will not react. So, how much nitrogen is getting in, that will go out. So, in this case how much is in, it is how much oxygen is used. If we know, then we can determine how much nitrogen is being used. So, that is equal to 0.79 by 0.29 into the moles of oxygen used. So, moles of oxygen used is equal to 44.66 which is supplied to the inlet gas. So, that is equal to 44.66. So, it is coming is equal to 168.01 moles nitrogen. So, this nitrogen we are giving here. Now, what will be the compositions of the outlet gas then? It will be having number of methane, it will be having which is unconverted, and the number of moles of carbon dioxide, and the moles of steam, and moles of nitrogen, and moles of oxygen which is not used. So, already we have got 1.222 for methane, for NCO2 we have got 51.78, and we have H2 we have got 63.356, and nitrogen we have got 168.01, and for oxygen we have got 6.504 which is going out. So, total is 290.87 moles. So, now we can determine the percentage. So, what will be the percentage of methane equal to mole of methane by total mole into 100. So, that way we will get it, and for mole of methane 1.222 by 290.87. So, this is the fraction. For H2O we are getting 63.356 divided by 290.87, that is 0.2178, this is 63.356. Okay. Then we are getting for YO2, that is equal to 6.504 by 290.87, that is equal to 0.0028, and for CO2, so 0.178, because this is equal to how much we have carbon dioxide. So, this is 51.78. So, 51.78 it will be divided by 290.87. So, that is equal to 0.178. Then we are getting say yn2 is equal to moles of nitrogen divided by moles of total outlet stream. So, that is equal to 180.01 by 290.87, that is equal to 0.5776. So, now we are able to get the composition of the outlet gas. So, our next problem statement says, so dry methane is burned with dry air, both are 25 degree centigrade initially, the flame temperature is 1300 degree centigrade, if the complete combustion is assumed, how much excess air is being used? The reaction is CH4 plus 2O2 CO2 plus 2H2O, and the standard heat of reaction is minus 8.028 into 10 to the power 5 joule per gram mole of CH4 reacted. Mean molar specific heat of gases between 25 degree centigrade and 1300 degree centigrade are in joule per gram mole K, that is equal to CO2 51.88, O2 34.01, H2O 40.45 and N2 32.21. So, this is the problem statement, and then what we have to do, how much excess air is required. So, that we have to calculate. So, how we can do it, let us see. So, what is the reaction given? CH4 plus 2O2 CO2 plus 2H2O. Then let us assume that number of moles of O2 in the feed is equal to Y, and the reference temperature is 25 degree centigrade, and the enthalpy of both CH4, O2 and N2 0 at 25 degree centigrade. This is where base case it is given. Then for complete conversion of methane, what is our condition? Say we have, this is our inlet, all are CH4, oxygen and nitrogen, it is there, air we are providing. So, nitrogen will be there, oxygen will be there, methane will be there. So, if we have 1 mole of methane, we are having Y mole of O2 and then 3.76 mole of nitrogen, because 21% is oxygen and 79% is nitrogen, that is why this mole ratio will be 3.76. So, if Y is oxygen, then 3.76 will be nitrogen. Enthalpy for all it is 0, and then outlet temperature is our 1300 degree centigrade, and in this case methane will not be available, but oxygen will be available because excess oxygen is used. So, how much Y is given? So, rest will be Y minus 2, because 1 mole methane consumes 2 mole of oxygen. So, Y minus 2 is the remaining oxygen, and then nitrogen, how much was available, that will be available here, there is no reaction with it. So, 3.76 Y, and then CO2, 1 mole of methane will give 1 mole of carbon dioxide. So, when 1 and 1 mole of methane will give 2 moles of H2O. So, we are getting 2 mole of H2O, and then enthalpy of these already we can calculate, that is equal to 34.01 into 1300 minus 25. Why? Because it is given that this value are given here for CO2, this one, oxygen 34.01 and H2O 40.45 and N2 is of 32.21. So, at the outlet all those gas will be available and their enthalpy values are also provided here. Okay, so, this we have to multiply by the moles into this one mCp dt. So, mCp dt, m with respect to mole. So, Cp is given here. So, this is our dt 1300 minus 25. So, this is our enthalpy value. Then we will get the heat balance, then we will calculate the value of Y, and that will be the excess oxygen required for this combustion. So, here accumulation is equal to input minus output plus generation. So, this is the heat balance we are consuming. So, input equal to 0, del H is not there because all are at 25 degree centigrade. So, that is our base case. So, minus output Y minus 2 oxygen is there. So, into 32.01 plus 3.76 Y for nitrogen, and then 32.21 plus 51.88 plus 40.45 into 2, that is the composition which we are getting, that is H2O and CO2 and then del T. So, this is your mCp and this is your del T, mCp del T, that is the output which we are getting with the gas stream, and generation we are getting, what is the during this heat is generated, that is equal to minus 8.028 into 10 to the power 5. So, by this accumulation is equal to 0. So, by rearranging we are getting this formula, and y is equal to 3.6416 moles. So, this is our y we are getting. So, then what is the excess air? Why this much oxygen was required? 2 moles was used stoichiometrically. So, 3.62 minus 2 divided by 2 into 100, that is 82% excess air was used. Therefore, 3.6416 mole oxygen was fed for each mole of CH4, and excess air was 82%. So, now we are able to solve the problems. So, up to this in this class, thank you very much for your patience.